Now we can derive an expression for c, the energy integral, by finding another expression for v squared. First, we realize that because the argument of pericenter is fixed, then theta dot is equal to the derivative of the true anomaly plus the argument of pericenter. And because the argument of pericenter is fixed, then this is identical to the derivative of the true anomaly. So v squared, which is equal to r dot dotted with itself, is then equal to, considering this equation, r dot squared plus r squared f dot squared. Now, if you take the equation of the orbit and differentiate it, then what you have is r f dot e sine f over 1 plus e cosine f. Now, considering the r square f dot is the angular momentum, and we found that the angular momentum was equal to the mean motion times the square of the semi-major axis times square root of 1 minus z squared, then we can take this expression, multiply and divide by r, substitute now this expression for the angular momentum, and now finally the equation of the orbit for r, and the expression I have with them is the mean motion times the semi-major axis over the square root of 1 minus the eccentricity squared e sine f. So let's clean this. So we have the velocity here. We have the expression for r dot. Now to find the velocity, we need to find an expression for r f dot. And we can do that because we have the expression for the angular momentum. We simply have to divide it in by the radius vector. So we found the expression for r dot and the expression for r f dot. Substitute both of them on the expression for the velocity, and you find v squared is equal to n squared a squared 1 minus z squared e squared sine of f, and then you square this term and expand it, plus 1 plus e squared cosine squared of f plus 2e cosine of f. Cosine and sine, they sum in a trigonometric identity, and what you have then is 1 plus z squared plus 2e cosine f. And now to advance here, realize that you can rearrange the equation for the radius vector and write 1 plus e cosine f is equal to a over r times 1 minus z squared. And this expression for the velocity, you can write as, you have a 2 in here, so you can sum 1 and subtract 1 to then have twice 1 plus e cosine f minus 1 plus z squared, or to put it under the same parenthesis, minus parenthesis 1 minus z squared, and then substitute the 1 minus z cosine f by a over the radius vector times 1 minus z squared. And you have 1 minus z squared on the numerator and the denominator. You can cut this. Now remember that mu is equal to the mean motion squared and the cube of the semi-major axis. So you can multiply and divide this by a, and therefore the velocity is mu 2 over r minus 1 over a. This is a very useful expression for the velocity, and for the velocity squared, the kinetic energy that is. Now, if you compare this expression with the energy integral, then you see that the value of c is this term cut to this term, and then I have c is equal to minus mu over 2a. So the energy integral is related to the semi-major axis. The energy of an elliptical orbit is a function of its semi-major axis alone and is independent of the eccentricity.